welcome to the second day. I want to go over a short presentation that I have, which is just called from logs to HCPV, or hydrocarbon per volume, which is a very short presentation that I have to put everything into context. To take a step back, we were working with the track display, and we were working with making inversion, and we always try to keep our focus in the end goal. But when we're working in the nitty-gritty, it's sometimes difficult to keep that in mind. So to take a step back and remember what are we doing and what is the purpose, I have this little presentation. And also to propose a method that we've been using in UTEP Wells for improving information evaluation and seems to be giving pretty good results. So first, according to the Wikipedia, very simplistic definition for formation evaluation. In petroleum exploration and development, formation evaluation is used to determine the ability of a borehole to produce petroleum. That's basically the only thing we care about right now. People are getting in, so let me just accept everyone. I have the chat open in case there's any questions. It seems like the chat is the easiest way. If you want to speak up, that's fine too, by the way, but it seems like it's easier. Some people might be in the office and some people prefer to just put in the chat. That's okay. I do keep an eye on it. All right. Anyway, back to formation evaluation. This is the definition we have according to Wikipedia. And we all are working just to determine, not only for this, but the main goal is to determine the ability of a borehole to produce petroleum. In many cases, this is reduced to two very straightforward questions. How much oil or gas is in there, and can we actually get it? These are two related but different questions that are answered differently. The first one is just answering how much hydrocarbon is there. What is the HCPV? The second one is answered by getting into the permeability. You need to know what is the permeability to know if you can actually get it, and then you can get more sophisticated and start doing economical analysis and so on. We're not going to get to this part. We will be working on evaluating how much hydrocarbon is down there. That's going to be the goal for today. Now the strategy that we have to calculate it using UTEP Wells is compared to the traditional approach. In most companies, most workflows, they do this simple analysis, which is perfectly correct. Only in some cases it doesn't work as well, and that's when UTEP Wells and modeling comes into place. The traditional approach, you just gather all the data, which is something we're going to do everywhere, as much information as you can get from everywhere. You do some quality control, and using the data directly, you can calculate porosity and you can calculate water saturation. And with those two, you got HCPV, straightforward. Now, here comes UTEP Wells, here comes modeling and tells you, well, sometimes the logs are not a true representation of the formation properties. We know this is true, and we know this is a problem. So if we know we are in a situation where this happens, we should do something else. What we propose is, well, the reason, before I go into what we propose, the reason why we have these issues are multiple, but they can be summarized into two reasons. One of them, the tools that are being used are different in some locations, and because they are different, they're going to give you different measurements that are with some issues intrinsic to the tool. Not really issues, but just the fashion, the physics of the tool is going to measure things differently. If you use an induction tool, or if you use a dual pack LDD or LWD, different tools are just going to show resistivity differently. And that's just how it works. So using the measurement of an induction tool or a lateral log the same way just does not make sense. So in these cases, we should model. And there's some intrinsic shortcomings of the tools. If the layers are too thin, they're not going to be very accurate. You see the resistivity horns. If the contrast between the two layers is too big, and there's many reasons why the measurements might not be accurate. Then on top of that, you have borehole conditions. The mud conditions might be different in different locations, and you want to put them together because you're using the same strategy to get all of them together, or you should. There might be different invasion conditions that, of course, are going to impact the measurements that you have. So you need to correct for all these things to get a better final answer. And deviation, that's, of course, one of the big issues that we have, and we've been having for the last 20 years or so in the industry. Things just don't behave the same way where you're in a horizontal well. Now that we know all the problems that you can have, let's actually propose the two-step strategy. First, let's stick doing the quality control the way we've been doing it. That's fine. Then, instead of using the data directly to calculate porosity and water saturation, let's rely on the Earth model that has properties that are independent of the tool and independent of the borehole conditions. And then we calculate hydrocarbon pore volume, and we're going to do it in a different way also than the way that it's usually done. So in a flowchart, we have the QC field data. Then you're going to invert for physical properties directly related to measurements. So this is what we were doing yesterday, and we're going to do a little more of that today using the Markov chain Monte Carlo algorithm, or whichever algorithm you may want to use. And then once you have physical properties, you're going to invert for petrophysical properties, which are the properties that are more closely related to formation. This should not say gamma ray and resistivity. This should say porosity, water saturation, mineral composition, and fluid composition even. So that's what we are planning to do. That's our goal. But before we do this inversion, or what we call inversion, we're going to learn how to do the forward, which is, in this case, is reverse. So going right to left. We're going to start from petrophysical properties. So we're going to start having a model that we give in the mineral composition, the porosity, water saturation, fluid composition. Then we're going to make it a little more, we're going to go up in scale. We're going to include the structure, if it has one, if it's laminated or not. And then we're going to calculate some properties directly related, or some physical properties. So given a certain composition, you can calculate physical properties. So you can calculate gamma ray resistivity and so on. And then once we have those, we can simulate logs. So in a way, we're going to go backwards first before we do we follow the order that is usually, well, the only order that would make sense in a real case. You start with the real data and you want to get the petrophysical properties. This is the only order you would actually do it. Something else that we're going to get by using this approach is that we're not just going to give you a final answer. We're going to give you the uncertainty that is associated to it, which, as we know, can be very important to make a final decision. And that uncertainty can be even associated to HCPV. So everything is going to have some uncertainty, similar way that we were doing it yesterday. Okay. Questions, comments so far? This method was developed in Carlos's group about 8 years ago, something like that. And people have been using it very, very, very much in a case-by-case scenario. And last year we were able to finally implement everything that needs to be implemented in UTEP wells to follow through. There are some areas that still have room for improvement regarding speed and regarding accuracy, mostly speed. But we can already do everything that we say that we have there, and we're of course working in improving the rest of the things. Now, like I was saying, we're gonna start by just looking at what we have. So I'm just going to add a new well. It's just a clean well, and we're gonna see what we mean by the composition. So we're gonna just build a very simple composition and see how that relates to everything. So I'm going to just make it a little smaller, just so that when I go into simulations, it becomes easier. So I'm going to say this set modeling limits to, I'm just going to make it 120, well, 1200 to 1220. So 20 meters. We're going to make it smaller, just 20 meters. And I'm just making sure that it looks okay. I'm going to add two more, 2 layers so that we have a boundary in the, so we have 3 layers. We have one in the middle. That is where we're going to be focusing on. And right now I'm just playing. So if you want to follow along. At any point you can start doing the same thing. And you, if at any point you have a question, go ahead and ask the question. So what I just opened is called the compositional palette, which is one of the staples of UTEP Wells. It's one of the oldest modules that we have, and it's one of the modules that make UTEP Wells UTEP Wells. This is what I call a high resolution model. You see everything with very high detail, and then you can upscale it, like I was discussing. To open it, you just go here. The third icon that looks like a painting palette is the compositional palette, or you can go in Earth Model menu and compositional palette, and you get this. So the first thing that I want you to see is down here in the bottom, it tells you the petrophysical layer where you're at, and then gives you a couple of options. Well, and you can navigate. You can switch to other layers. We have 3 right now, and it just tells you what is the top. So you have an idea of where you are regarding measured depth. You can also go one by one, and when you switch, you may calculate bulk properties or may not. It's up to you. If you don't, it just switches back and forth really fast. And you can see, but also here in the track display, you can see that this tan is showing you where you are. And this is convenient when you have a well, just to know where you're the composition that you're seeing, where is that related to the entire well. Okay, and of course you can switch. You can make bigger jumps from here. So this is just navigation. And if you say calculate bulk properties when switching, anything that you have here, and I'm going to go back to anything we have here, is going to be calculated based in what we have in the petrophysical calculator, which is the tab right next to it. For now, I'm just going to say things are calculated. We're going to get back into the petrophysical calculator in a little bit. And then you can also save in multiple wells. That's if you have a composition that you want to save in, multiple layers, you click here and you say, well, 1 and 3 are the same, and you just save it. And even if you, without switching, you want to just calculate the properties, you hit here, and that's all. Okay, then here you have a volumetric reference that tells you how much of the volume is matrix, how much of the volume is porosity, and how much is water saturation. If you had shale, it would show here. Somebody's trying to get in. Let me just allow them. So I have a quick question here. How do I switch from feet to meters here? You go into in here the units of measure, and you just click here, and you could switch from meters to feet. Yeah, this is actually important. And you just say apply, and everything changes. And if you say OK, it changes and closes. That's how you switch units. Okay, so yeah, so just to reiterate, it's the icon that has the FTM, is feet to meter or something like that, units of measure. Now, so back here. So we have the matrix, and we have the water saturation, and the rest of it is just hydrocarbon. Now, on top of it, we have this panel that refers to the structure. Everything we do in UTEP Wells refers to Thomas Tybur structures, but related to structure, we have 6 properties that are very, very much interconnected when you're working with the Thomas Tybur diagram. First, I'm just going to go over the properties, and then I'll go over what the Thomas Tybur diagram does. So here we have just total porosity, and you can modify it here just by typing, or you can use these arrows if you know what if you want to do that. We have the matrix porosity, we have the shale porosity, we have the shale concentration, and then these other two, lamination factor and Shaley factor, are they're completely dependent variables on the other four. And they only make sense when you're in laminated, when the structure that you have is laminar dispersed or laminar structural. Now, the Thomas-Tibur diagram, as I think all of you know, the Thomas-Tibur original paper was non-shale concentration versus total porosity. It was gamma ray versus, I think total porosity actually, but gamma ray. Instead of shale concentration, he was using gamma ray. Is just a different space. We just this also makes sense. There's many versions for it, but this works too. And so we have shale concentration and we have total porosity. We have these little asterisks here represents the combination between total porosity and shale concentration. Of course, this is going to be very much related to matrix porosity and shale porosity. So in the very left, we have 0 shale concentration, which means if there's 0 shale, it's pure, is clean matrix. So this dot over here is going to be representing the case where it's clean matrix. And this dot over here would be pure shale. And then in between, we have a number of cases. If we go in this straight line, well, it's probably easier if you click in this button, you get some cheat sheet that helps you understand everything we're doing. So here in this blue line, which is exactly the same color as we have there, you're in pure laminar, meaning that you're going to have shale and clean matrix one after the other, one, without having any mix. And that's going to give you, of course, very high anisotropy. In some cases, this is what we observe. Then we have another ideal case where we have 100% dispersed, or idealized cases, which happen to be pretty close to some physical systems. In this case, it means that you have the matrix as grains, and around the grains in the matrix porosity, you have some shale that has grown there. And you would stay only in this line. And the top here, we have structural, which means that some of the grains in the matrix have turned into shale, just time and weathering. And you're going to stay in this other line. So in that case, of course, porosity goes higher up the more shale you have, because shale is going to have its own porosity. And well, in any case, if you don't remember how this works, you just click in this button and it opens up. It's actually pretty useful. Now, you may want to enforce that structure. So if you know that in that layer that you must have dispersed shale or clean matrix, you can just click here and it's going to force you to be in that area. So for example, in most cases, you have dispersed. So if I try to move, this dot is going to stay, is going to force all 6 properties to be coherent. So matrix porosity is going to be modified as I move around here to keep everything consistent. But if you don't want to enforce it, it's okay. In some cases, you are over here. It might be also just a guide to know how things are going. In most cases, I think that's how people use it. But once you're making some analysis, some people may want to enforce that structure. So you can do that here. And you can also just enforce non-shale porosity, which just means, that one actually makes a little more sense. It just says, or it makes more sense to enforce it at all times. However, if you're enforcing structure, you're also enforcing this one, by the way. And what this one means, just that so this is the help. When this is checked, only combinations that yield a non-shale porosity between 0 and 1 are valid. And that's just using the equation right there, that the non-shale porosity has to be total porosity minus shale concentration times shale porosity. So it's just this is a physical limitation. This is a real physical limitation, so it always makes sense to have it checked. This one is a little more idealized. The Thomas Tiber is a little more idealized, so sometimes it's okay to not have it checked. And this non-shale porosity limitation from just this point of view is just making sure that you never go after those two lines. But you can be out of the diagram here. It just means that you have low porosity and low shale concentration. That's okay. That can happen if you had a grain size distribution that is very wide, that you have very small and larger grains. You could be over here, and that'd be okay. Am I missing something, Bruce, in here? You can also zoom in and zoom out, and you hardly ever will go up here, but you can.
Yeah, so I don't know if you pointed out that the black dot you see there is what this particular layer is assigned to.
Exactly. Yeah. So this black dot, black asterisk is what we're assuming the physical reality is. And whenever I move it, you can see that the volumetric reference is modified and this is modified. So we're starting from the very bottom. So we're deciding what is the matrix, the total porosity, and all these properties from a volumetric point of view. Now you can see that we have shale, and next to the shale we have some porosity or some other color here. This darker blue is just the shale porosity. By the way, you can on top here to the right, you can check that and see things as non-shale. Some people prefer to see non-shale instead of total. So this is total porosity, or you can have non-shale porosity. And this just for visuals. So there we assume that shale always has intrinsically porosity. This last workshop that we had in person, we had a discussion between Andreas Kinsley from Wintershall and Carlos that was actually really interesting. Every time we present this, people complain. Well, not complain, but they say that it's not really shale, it's clay, and some people say no, it is shale, it's not clay, and we have this back and forth. It's very difficult to keep everyone happy, and the discussion we had was very interesting to see what we really mean and why we have it this way. And in a few words, this is shale for sure. It's not clay. It can be used as clay in some cases, and we know that in many interpretations it's easier to reference clay than to reference shale. But this is really shale, and the composition that we have here for shale is up here. And you can have any component. So you may have clay components, and by default, in this version, we have illite, which of course is a clay, but it doesn't mean necessarily that it's only clay. You can add a solid, and you can have that be chloride. Well, I'm going to more clay. It could be a carbonate, it could be quartz, it could be anything really. So you have full control on what a shale is.
I think one of the things that Ali was mentioning is that we may, because of the way that the two different types of shale are generated, I mean, between the laminar and the dispersed, a lot of times that they can be completely different. Like the dispersed shale could be just pure clay, and then the laminar could be clay mixed with quartz and other elements and stuff like that. So we may eventually want to have two different compositions for that.
Yeah, we may. That's true. We may want to do something like that. So we have a question. So working with this model assumes that I already know what is composition of my reservoir, correct? Correct. Now, again, we're going from bottom up at this point. So we know that in most cases, you do not know exactly what you have in your reservoir. But after we go from small to big, we're going to go big to small. So this morning, we're going to go from here to logs. And this afternoon, or in 4 hours, we're going to go the other way around. We're going to go from logs back to here. And of course, it always helps to have that QL that has extra information that at least gives you an idea of what you can have there. It's going to be a lot better if you at least have some idea. But the way we're working in this modeling right now, yes, we are assuming that we know everything. It's this morning I'm just going to work with synthetic models, which allows you to do whatever you want. And if I start from bottom up, it's very easy to keep it petrophysically consistent because, well, if I know the composition, I can calculate all the properties, and those properties are going to be reflected in the logs. For sure, it's compositionally consistent because I started from a consistent model. Now going the other way around, that's different. It's a little more complicated.
Joaquin, can I ask a question?
For sure.
So when your little asterisk is moving around in the Thomas Diver crossplot, how do you get that to happen?
If you what? Sorry.
You're able to move your point around within the diagram and it's showing you different numbers.
Make sure you uncheck the enforce structure.
Okay.
And then just grab it. You can just go over it. At some point, it's going to show us a little hand on top of it, and you can just move around.
I mean, either that or you can pick a different structure. For instance, if you want to move it around freely in the laminar dispersed, I mean, you just have to select laminar dispersed.
Yeah.
And you can...
I was seeing that it looks like where your cursor is in the diagram is bringing different numbers up below, but I didn't have that.
It's not showing different numbers down here.
Yeah.
It only will show them when you release it. I don't know if that's the problem. Maybe not.
Okay, I see what you mean. And another question, how do I get rid of a petrophysical layer?
You just click here and bye-bye.
Sorry, I missed that.
If you click in the X here, the delete bed or radial boundary mode, and then X that.
Yeah. You don't really delete the layer, you delete the boundary. Layer.
Okay. That's what I thought. It didn't seem to be getting rid of my upper layer, but
yeah, let me see if I delete this one, then this gets updated. Now it's petrophysical layer 2 instead of 3.
Yep.
That's okay.
Thanks.
Then if I add one, then it goes back up. That's okay.
I think it takes the top layer and brings it down or something.
Yeah. Yeah, and then it changes to 2, but that's okay. So we're in 3, and this is the one we're playing with. So the shale composition, you can have, so like I was saying, it can have any mineral. It can have quartz, zeolite, clays, carbonates, can even have carbonates. And it also has a porosity associated to it, which you set up here in shale porosity. And it has a fluid. In most cases, it's going to be just water. I don't think I've ever actually worked with a case that has something else. Someone will probably have a different experience, but in shale, it's most cases just water. And if it's something else, you can just choose it here. You can add a fluid, you can modify that. You have to make sure that it's consistent. So we can normalize to make sure that the total amount of elite and quartz adds up to 1. You have some salinity associated to it, which is just the salinity within the shale. It's not the same as in the rest of the fluid. And you can always reuse components. Let's say that this is a shale. This composition is close to the shale that I see in my field. So I can just call it field shale or whatever, and just enter. And it's going to be an option here, field shale. These are some that have been used in the past. I don't even know at what point they were added, but Winamata, elite and quartz. You can, anyway, so these are predefined cases. Also for the salinity, you can have any amount of salt. You can modify it with this, and we have these other advanced options for shale salinity, which allows you to use other types of salt, and other types of salts are going to have different effects on the model. By default, it's just sodium chloride, but we have these other cases. This one was this salt was the reason why we started doing this, because of course it has very different properties regarding density and resistivity. The 2 properties that are going to be affected are density and resistivity. And we actually had pretty good, it's a successful story because we did it with I think Wintershall was the company, not Wintershall, Woodside was the company that needed this, and we did it for them. But it was open, it was for everyone. And then some people from Petrobras, without us telling them anything, they started using it, and they were actually very happy because they were getting better results than with any other models that they had. Anyway, of course, we have to brag a little bit of the success we've had in the past. So that was. So salinity can have higher resolution than just sodium chloride. So that's the shale composition, very high resolution. And similar, we have the same for the matrix composition. And the matrix, I know again that the wording in the field is not always 100% consistent. What we mean by matrix is just the grains of the material that you may have. Not I think Bruce was proposing just calling it non-shale to get away from this discussion, but it's always, there's always going to be someone that's going to say no, it's not exactly non-shale or something. So we are stuck with matrix, and as long as we all understand what it means, it's good enough. And we have some predefined matrices. We have sandstone, we have limestone, just calcite, of course. We have dolosand, and we have other cases that have been predefined. So let's just say it's calcite, and you can have more. And you can rename it the same thing as with shale. And these two are going to define all the minerals that you may have. Besides the minerals, we of course have the fluids. And within the fluids, we have a little more of a navigation area, where here you could have, let me show you actually a couple of tricks here. I'm going to add in between a fluid layer. And I think I need to refresh it. No, it's not showing it. No, I know why it's not showing it, but it's saying the entire petrophysical layer. So I have to unclick here. If I have these two are saying that whatever properties I have here are going to apply to the entire petrophysical layer or to all radial zones. So I uncheck these two, and I can see I have two property layers. I have 3 and 4. Within petrophysical layer 3, we have layer 3 and layer 4. Property layer 3 and property layer 4. We only have one radial zone. I'm going to add here this display. I'm going to make this larger. So we have the borehole and we have the formation. You do not access the borehole through the palette, just the formation zones, invaded zones they may be. I can add a radial boundary here, and now I can see I can move to, there's 2 radial boundaries here. There might be 2, these 2. So within all the rocks are going to be the same, but the fluids can be different in these 3 sections. Okay. Now for simplicity, I'm just going to say the entire petrophysical layer, and I'm going to delete this just for simplicity, but you can play with that. And it's just to show you that you can do it. That's it. Now here you have the water saturation that you can just type, let's say it's 9, just type 9 and you get the water saturation here. You can also play with, by the way, the volumetric reference is not just, it's interactive, so you can play with it. Of course, a shale porosity that big wouldn't make sense, but anyway, you can play with it and make sure that everything is well, that it's closer to what you expect. You have the salinity that by default is really large, is 100,000. Let's say 30,000 might be better. Maybe the shale salinity is okay at 100,000. And again, you can modify the salinity breakdown for this case. Then you have a temperature and pressure for this layer, and you have the fluid density. And if you modify the temperature, you're going to modify the fluid density, and the same thing with the pressure. If you make it warmer, it's going to get lower density, and similar with pressure. And then similar to what we have for shale and matrix, we have a fluid composition. By default, we have this oil mix that includes these two hydrocarbons, but you can modify these to be methane or any of these. You can add a component, you can normalize the same thing as the others. Okay, so now once you've set up a layer that looks like what you want, maybe the 12 porosity is too big, let's something like this. Once you're happy with what you have here, or you can calculate the bulk properties. And when you hit calculate bulk properties, it's going to calculate whatever you have here. So I'm going to go over these options. The first one is whether to enforce structure consistency or not. Any of these are all the calculations that can be done, the ones in the left in this version. If it's checked, it's going to do it. If it's not checked, it's not going to do it. So if I don't have anything checked and I say calculate properties, it does nothing. But if I have the enforce structure consistency, and I say this has to be dispersed, for example, if I calculate it, and I can calculate it here, or I can calculate it here, by the way. And you saw that this got modified. So I can just say calculate, and it's you need to do this. It gets done there. Okay, so that's if you want to enforce the consistency. Also, we have a couple of projects with the students and with some sponsors where it was very important to have the consistency right. And it's very tricky when you are deciding which property to modify to get the other ones right. So this is just the enforcing order, which means that the further left is the less likely to change, the further right is most likely to change. These are the ones that we think are more commonly used. You would want to keep shale porosity for sure, shale concentration, total porosity, and lastly, matrix porosity is almost a fake property. So in most cases, we put it at the end. So you can modify it according to these preset orders, or you can just make your own order just by saying, well, I actually care less about shale porosity than matrix porosity. You can do that, which would be an interesting case. Most cases, I think you would do something like that: shale porosity, total porosity, shale concentration, matrix porosity, and just say okay, and that you would have in here. It's just an extra option that shows up there. Anyway, so you can do that. That one is, most people don't use it, but it can be or it's not such a standard in the industry, but it's actually useful. Then the bulk nuclear properties, which is an industry standard, you can do it using, we have three different structures. We have solvers. We have SNUPAR from Schlumberger, which I would be hard pressed if anybody hasn't used it in their life in the audience. Then we have WeatherForce RAPM, and we have our own UT-NuPro. They all do pretty much the same thing. SNUPAR is the most commonly used, and UT-NuPro is almost a follow-up of SNUPAR. It's a little more recent. It was done 4 years ago, maybe 5. Some of the SNUPAR was done like 15, 20 years ago. So just because of timing, UT-NuPro has higher resolution in the tables that are used to solve all these equations. So it's a little more accurate, and it's a little bit faster. In the newer version, it's significantly faster. And by the way, some companies were asking for, I think it was Exxon, if I'm not mistaken, but so they were asking for a standalone version of UT-NuPro because they want to incorporate in their things. They want to run it independently. So we're working on that. So if you're interested in getting UT-NuPro without getting the entire UTEP wells, it's also a possibility. Anyway, that's an extra side note. Now, the source types that we have, you can run AMBE or 14 MEV, or both of them. And what these are going to calculate, if you ever forget which properties, you can just go there, and that's going to show you. It's going to calculate thorium, uranium, and potassium concentration, which is those together make gamma ray. We're going to have also bulk density, we're going to have the photoelectric factor, migration length, hydrogen index, and neutron porosity. Neutron porosity only SNUPAR and AMBE, and we have sigma, the thermal neutron capture cross section. All this is calculated if you calculate the bulk properties. I'm going to focus in these two. We're going to play with these two in a little bit, or let's play with these two, and then I'll just briefly mention these two later. So I'm just going to do, if I hit calculate here, it's going to do that calculation in all petrophysical layers. If you want something else, you can just select it here. But now, because it's a very simple model, I'm just going to do all 3 layers. So now I calculated everything. Let's make it something a little more interesting in the palette to see some interesting results here in the track display. So let's say that we're going to have some shale. I'm going to say that I have pure shale. It's very idealistic, so bear with me, but it's going to make sense. Pure shale, which is illite and quartz. This porosity, we're going to say yes, it's a 0.06. That makes sense. Salinity, the salinity is not even going to be taken into account. This is the only one that matters. This, we're going to say that makes sense. And I'm going to save it in multiple layers. I hit save. So now I got the waiting bar in my other window. Now it's saved in this too, and it also calculated. Calculate when saving, make sure that everything is being calculated. So now, so if I go to layer 1, it's going to look exactly the same because that's what I put. Now, if I go to layer 2, it's going to look different because we have not modified that. Now, in layer 2, let's make this limestone. Or let's make it limestone. And let's say that the fluid that we have is some gas. So let's say methane. Let's make the water saturation lower, 0.1. Temperature, let's say that this is okay, that the temperature and pressure are fine. Now I'm going to calculate bulk properties. So everything's been calculated. Now let's see what it looks like in here. Sometimes the delete leaves some lingering graphics, but it's okay. We don't need them now. So we calculated, for example, gamma ray. So I'm going to include our Earth model. Right now we're only working with the Earth model, and again we're going to be working only with the Earth model. We're making these from small properties, from petrophysical properties to physical properties, and then we're going to run the simulations, which is going to get us the logs. So gamma ray, okay, and we can see that it makes sense. I'm going to get rid of the tan because it gets in the way for this explanation. So I just click here and it goes out, it goes away. I know that I'm editing this layer. So now we see gamma ray is higher, much higher for the shale layers than the sand, than the limestone layer. That makes sense. That's okay. By the way, when we are working with gamma ray, we know that gamma ray is coming from these 3 concentrations. Really, what you measure, you don't measure gamma ray because that doesn't exist. You only measure concentration of potassium or signature of concentration of potassium, uranium, and thorium. That's all you can measure. And so within the Earth model, well, and then you calculate it modifying one or the other. So within the Earth model, if you modify potassium, you will modify the gamma ray concentration. And the way that it's modified is by making by using some coefficients that we're going to talk about tomorrow. But there are some coefficients, or actually later today, right, Bruce? You're going to talk about them in nuclear. When you do nuclear modeling,
yeah,
right?
comes up next.
Yeah. So right next, we're going to talk about them. So I'm just going to say that they are connected. And let me just calculate properties again, so it's where it's supposed to be, and that's okay. Now, we also calculated, besides gamma ray, we also calculated neutron porosity. This is the other one that I want to show you. A neutron porosity, we always assume that is very much related to migration length. So we have migration length that has been calculated, and we see that the migration length, let me make this a little thicker. It's not looking very good. Now it's a little more clear. So we see that migration length was higher in the sandstone, or in the calcite, actually, limestone, which makes sense. We were not used to thinking on migration length, but in UTEP wells, I could say historical reasons, we work with migration length more than with neutron porosity, but they are the same. They are the same property, really, migration length and neutron porosity. Neutron porosity, limestone, AMBE, and it's they work in different directions, so that's okay. So I'm just going to make this 0 and let's say 0.6. That would be okay. To have neutron porosity and migration length. If I modify one, again, I modify the other, because they are really they are the same property. They just it's two ways of seeing the same property. That's okay. Now, next to migration length, I may want to see, sorry, neutron porosity. I may want to see actual porosity, for example. So I'm going to add Earth model porosity, total porosity. And I'm going to keep the same. I'm going to change the color because I don't see those two colors very well. And you can see something interesting. You can see that where we have the gas, they do split, but here they are also not completely matching, because, well, we have shale, so of course they're not going to match. That's fine. Something else that is important in this case is that when you run the nuclear properties calculations, you can have you can choose to take into account the salinity, temperature, and pressure, or not. In most cases, you do want to take into account salinity, because that's going to influence everything. And the service companies they typically don't correct for this, but they typically do correct for temperature and pressure. So you typically don't take into account pressure and temperature. But if you were working with raw data, you could take them into account, and then of course the results would be slightly different. You see that they moved a bit, because now they're taking into account temperature and pressure. And if I don't take into account salinity, they're going to be vastly different, or the shift is a little bigger. I don't know if vastly, but a little bit bigger. Any questions here? This is something that we're going to be using a lot, or sometimes we're not going to see that it's running, but we're going to be running it a lot in the back. Okay. If there's any questions, just put them there. And just briefly, I'm going to mention we have effective medium theory, which allows you to calculate slowness for your layer, and it works in a rock class level. I'm gonna go into what rock class mean, and we have a number of models. Basically, the entire rock physics book by Mapco is here. You decide what you have, and it's fairly straightforward. So I don't want to spend too much time, but I do want to mention that we have it. And for NMR, we also have calculations that are rock class dependent. And we're gonna go into this a little bit Wednesday. So I'm just gonna leave it as is for now. Okay, so now two things I want to show you are first the rock classes. Here in the palette, you always have a rock class that you have associated to each layer. Each layer always has a rock class associated. And by the way, we also have these extra porosities that we didn't even talk about them, but they are going to be more useful when you work with fluid flow. So I'm not even going to go into them, but they exist. Residual gas, or oil saturation in gas, and so on. Anyway, so every layer has a rock class associated to it. And you can see what are the rock classes that you have. Right now, you always have at least default, but you can have a new rock class that has different resistivity models. This is Archie and similar. So you can have UHAST, which is default, or you can have Archie, you can have Indonesia, and so on. You also have the Timur models, Timur Mixed, Timur Tixi, or modified Timur codes. You also have the PCKR Studio. You have the effective medium theory. This is PCKR Studio is actually really interesting, but we're gonna work with it on Wednesday. So again, I'm gonna leave it like that. So this is just suppose that you have two different rock classes, that one of them has UHAS, the other one Indonesia. You can of course modify any of these parameters, and you could assign either one of those here. Okay, I think I covered most of this. I have a little exercise that I think we have enough time to do it. Did I miss anything, Bruce, or questions?
I didn't see anything that you missed. Looks like you covered all of it.
Okay, good, thank you. So here in workshop materials for Tuesday, we have resistivity and isotropy, and it's the one that I'm going to follow. So if you want to follow along, this is what I'm following, or if you want to follow along later, this is the one I'm looking at. Okay. So I'm going to close this well, and I'm going to start with another well. Now, the objective of this exercise is to practice building an Earth model that are consistent from petrophysical point of view. In particular, we will see the relationship between laminar structure and anisotropy in resistivity. So we're going to do, first, we're going to modify the reference track limits to 0. Well, let me put it here so you see what I'm looking at. That window doesn't allow you to do that. Okay, so I'm going to go from 0 to 150. So set reference tracks 0 to 150. Okay. And then I'm going to add 4 boundaries to make 5 layers, so approximately 20, 40, 60, 80, 1, 2, 3, 4. Actually, it should be 25 to make 5 layers. Yeah, this is okay. So we just need to have the modeling interval is smaller. This is okay. So we just need to have 5 layers, five different layers that I'm going to be working with. And let me make sure that the modeling limits are, they're consistent at 0 to 150. That's okay. And the exact location doesn't matter. I just want to have enough to show. And some people is. So I have a question. Will the model use RH and RV from 3DEX or MCI? Yes. Yes, we can. We're gonna do exactly that. We're gonna generate RV. So the question is, will the model use RH and RV from 3DEX or MCI? So we're gonna do the opposite. Right now, we're gonna generate synthetic RV and RH from from the anisotropy that we have in this well. If you were going to go back from R3DEX or MCI, you would be able to have both resistivities, RH and RV. Yep. So now I'm going to show you another way of looking at the data, which is called the table view. The table view is exactly that. It's just a table that allows you to see properties that you're going to use anywhere else. So from the compositional palette, we set everything here, but we want to, for example, compare all the porosities. So it's porosity, shale concentration, porosity. So basically everything related to the structure. Okay. So you just need to choose here the properties. So I'm just doing porosity total first, then shale concentration. Then I'm doing porosity. For shale. Then I'm doing porosity for matrix, which is really, it's like I said before, it's almost a false variable, but to make sure that we have everything in place, we should do it. Then we have water saturation. Total. And lastly is going to be the shale structure, which is the same as what we had in the Thomas-Tybert diagram. So in this case, we're going to have 5 layers that are going to have the same total porosity. They all are going to have 0.2 total porosity. So I just type it there. And by the way, you can save this as CSV, which is Excel readable. It's comma separated value, but you can open it with Excel. So it's pretty useful in some cases. So the entire table can be saved. You can also copy and paste with Control-C and Control-V, just like you would do in most programs. Just copy and paste. Now the shale concentration is also going to be the same for all. It's 0.3, right, Bruce? Okay. Have a
The shale concentration, I think that sounds a little bit high. Oh, I guess it's right. Okay. No, it's yeah, it's shale concentration.
Shale concentration. Yeah, that helps me read. Okay. Apologize for the sizing. So all of them have the same porosity and they all have the same shale concentration. But we're going to see that they give us different signatures. And that's the point of this exercise. So you have shale concentration, total porosity. Then we have the shale porosity. The first one is going to be a very tight shale, 0. The top 2 have 0. Again, it's synthetic. It could be 0.2 or 0.3 to make it more realistic, but the final answer is going to, or the final result is going to be the same. So let's stick with 0. And then the bottom 3 have 0.1. Then the matrix porosity is going to be, we're not going to play with it. It's going to be enforced given the shale structure. But water concentration is going to be 0.6. We actually want to make sure that it is 0.6. I'm just making sure it's 0.6. And each of the layers is going to have a different structure. The first one is going to be dispersed. Then we're going to have 2 laminar. So we will see anisotropy in these 2. And then we have another 2 laminar dispersed. So the difference between, well, the first one is just dispersed, is what most people assume in most cases. Then it's laminar with the same porosity, same shale concentration, same everything, only different structure. Then the second one is the same, except there's more porosity in the shale. The total porosity is still the same, but most of the porosity, there's more porosity in the shale than everywhere else. And then we have laminar dispersed following these two. These two should have different matrix because in laminar dispersed, if you remember, you have more freedom for the matrix porosity is not completely set. So they're going to be the same, except the matrix porosity is going to be different. So first, let me try to do this, just enforcing, and I'm going to enforce the structure consistency. I don't need to do this. I'm just going to enforce structure consistency, and that is going to calculate. If I go back to the table view, I can see that the matrix porosity has been changed because in these two cases has been changed because laminar fixes the matrix porosity. So it's changed and it's to the numbers that are supposed to be. Here I have more freedom, so I'm going to write the numbers that we're supposed to have, 0.3 and 0.42. And if we look at that from the palette point of view, I'm not going to calculate anything. I just want to see 4. So 4 and 5. It's the same, except the matrix porosity is different. The location of this black dot is the same in both cases, but the matrix porosity is different, and that's going to give us different anisotropy. Okay, so now that we have everything actually set up, we don't need to enforce, we can leave it on. And if it's on, it's going to do first this one and then this one. And now let's do the bulk nuclear properties using UT-NUPRO.
I think that was a good opportunity to see the dependence of the shaliness and the laminar coefficient when you went back and forth between those two.
Oh yeah. Yeah, the lamination factor and the Shaley factor, that, yeah, thank you, Bruce. You can see that you're not allowed to modify them, but if you go between one and the other, they don't seem to change.
They should. No, maybe they're not getting updated.
Yeah, we'll look into that. Anyway, so we're going to calculate the nuclear bulk properties using UT-NUPRO. It's going to take a second, but it shouldn't take too long. And once we have done that, we're going to calculate also resistivity. And we're going to see how they change. So besides these two, we can also calculate here in the right, we have other calculations that we can do. So we can calculate resistivity. Yeah, just calculate resistivities, right, Bruce? From water saturation. Yeah, just calculate resistivities using the models that we have. And in this case, it's just default. Let me make this a little smaller to make sure that we're doing everything right. Yeah. Right. Yeah, it's okay. Okay. So I just hit calculate and it's doing the resistivities. Now we're going to see how they look like in the track and in numbers. So here, Earth model, I can do resistivity, parallel or homogeneous. Yeah, it's looking okay. And also resistivity, but perpendicular. And we see that they are, of course, not the same. And we should see it logarithmic. Maybe 2 is good enough. I don't know if it's just me, but I really can't see those two colors. Now you can see that, as we expected, the first one, they overlap on top of each other because it's dispersed, so no anisotropy whatsoever. Then we have two laminar cases where we see the difference between these two. We see the higher anisotropy where the shale has no porosity. And then we have a laminar dispersed where you see a little less anisotropy, and laminar dispersed with more matrix porosity with even less anisotropy. Besides looking at the results here, if you have any questions, do let me know. so besides looking at the results here, we can also look at them in the table. So we could add yet another column and say, I want to see resistivity as a number, just parallel or homogeneous, and perpendicular. So RV and RH. And you see, from a numerical point of view, how they are different. And by the way, any of these tables that you're using, you can save the group permanently, so you don't have to redo everything. And you can, well, there's all these other controls, only modeling interval or averaging petrophysical layers. This in case you have invasion. Now, the last thing I wanted to show you here, it's more for user friendliness, or another option that you have is, besides looking at the numbers here, you can add a track, and in that track you can add a plot called numeric, and it's the same plot as we have here for the measured depth, which, by the way, you can see measured depth, you can see true vertical depth. You can hide, you can mask depths that can be useful. We don't talk about this one much, but I know that it's actually something people use when they're going to present this in different projects. But anyway, so you can mask the depth, you can choose the precision, it's pretty flexible. Now, what we want to see is the resistivity, just so that we see how it looks like within the track. So it can be precision, very significant figures, something like this. And you can see in this layer, resistivity is this, and so on. It's just, it can be useful in some presentations. And I think that's it. I don't know if there's any more questions or comments. I think it's not too complicated, and right now it doesn't, I mean, depending on what your goal is, it might look very useful or not. If your goal is to understand a little bit the physics or the petrophysics of the system, this can be very useful. I know a lot of people use this part of the software also in teaching sessions, and I hope that part is understood. But then, probably more importantly, we're laying down the foundation so that later today we can go in the opposite direction. We can take physical properties, so take resistivity and go from resistivity back into this complex model, or
I think regarding the question on the 3DEX, I mean, that would give you a log that would show RV and RH.
Right.
But you'd have to kind of have it. I mean, it simulates from the Earth model, so you kind of have to have it in the Earth model first, and so you kind of have to do something like this first. Unless you had the logs, if you're external logs, you could use those to populate these. It kind of depends if you're talking about the simulation or you're talking about an imported log. Because if you're talking about an imported log where it's one of the logs that you have from your data, then you can use that with the property, or with the populate properties, to fill in this RV and RH, and then you'd kind of be going the other direction rather than calculating RV, RH. But if you want to use...
I think he means the first thing that you said, because 3DEX can give you RH and RV. So yeah, you can use it to populate these properties in the model.